The resistor has been supplied with a 8.5 kilowatts uh, energy at a steady state. So we are supplying this energy at a steady state. And what does it mean? So if I draw this system, this is the resistor inside a furnace, and here this is the air. We have air over here. This is the air between the resistor and the furnace, and also here also air. And this q is supplied to this one. Q dot is supplied to the resistor, and the same amount of q dot is coming out of the resistor. That is what this steady state means here. So, and here this furnace is receiving this q dot from the resistor, and the same amount of q dot is it's giving to the atmosphere outside the furnace. That's how these TF and TR will remain constant, because these are in the steady state. So whatever the energy they are receiving, they are exactly giving the same amount of energy. That's how they are keeping the steady state here. And here in the problem, we need to consider the resistor as the system. So I have considered the control volume around the resistor here in the red color. So that's why we have only one Q interaction, that too with the air. Why? Because if you consider this resistor inside the furnace, it is like a small body inside a big room. But whereas if we are asked to consider this furnace as the control volume, this as the control volume, then this is interacting with the two sides. That is one side, air inside this furnace, and on the other side this air existing outside of the furnace. So in that case we need to consider these two interactions here. But whereas here resistor, we need to consider only this q interaction with the air here. And in this case we know the exergy balance. In any control volume we can write the exergy balance equation. This is the rate of availability equation derived by using the first law of thermodynamics and the second law of thermodynamics, and also by substituting the value of this availability in these first law, combined first law and second law of equations here. But here in this case, since it's given as a steady state, and what happens here? So first of all, let me define what is the exergy. So exergy is the ability or the availability of the or the potential of the fluid to give proper useful work. So what does it mean? How this is different from the energy? For example, if I take a steam, the steam I will take at two conditions. In the first condition, steam is at the 200 degree centigrade, and in the second condition, this is at the 150 degree centigrade. And in the both cases, I executed some process such that exactly 50 degrees temperature got reduced. So when the 50 degree centigrade got reduced, and if I calculate delta E in the both cases, these delta E are same in the both cases. But whereas the quality of the steam at the 200 degrees is of course obviously different from the quality of the steam at the 150 degree centigrade. That means the steam, even though it produces equal amount of energy by executing the process of reduction of 50 degrees, the ability of the steam at the position 1 is more. That means it can produce, if it is allowed to expand up to the atmosphere level, which is a dead state, then it can produce more work. It has more ability to produce work. But whereas in case of state 2, its ability is a little bit lower than the stage 1. So this potential is given by exergy here, but not by the energy. So that is the basic difference here. That is the exergy here. And here in this case what happened? And exergy, whenever exergy reaches the dead state, that means whenever it goes to the in consonance with this atmospheric conditions, then it will become useless. But here in this case, what is happening? So we are providing the resistor with the q dot amount of the energy. So it is having some potential to produce some work, that is it's a exergy. But here what is happening, the same amount of q dot is coming out of the resistor, we are not utilizing anything. So what is happening here, that means we are the potential of this q dot is destroyed, got destroyed. Why? Because we are not using anything here, the potential is simply got destroyed. That means the exergy is destroyed here. Why? Because we are not using this supplied energy. So whenever the exergy got destroyed, that is nothing but a irreversible thing. So here del exergy of the input is equal to exergy of the output. So when exergy of input equal to exergy of the output, it becomes 0. Why? Because this is in the steady state. So if I write here in the steady state, what is happening? Steady state, if I take energies, so energy in minus energy out, what is happening? Energy in and energy out, that is a 0. Why? Because here energy is conserved here. So there is no loss in the energy, whatever energy we are giving in, the same amount of energy is coming out. But whereas if I take the exergy, so exergy in minus exergy out, this is got destroyed. Why? Because the potential, whatever potential we have given to the system, it is not been utilized, but simply it's rejected from the system. That means the potential is rejected, we haven't used the potential. Then whatever potential is rejected, whatever we haven't used, then it all converted into irreversibility here. So this is all irreversibility. So in the steady state, what happened? The energy is conserved, but whereas the exergy is got destroyed here. So this is not conserved but destroyed. Why? Because once the exergy out, this is out, reaches the dead state or reaches some other state, then it never can take back to the original position. That's what we learned in the availability chapter. So this is exergy is out, and this never can take back to the exergy original or the input, so that our potential or its potential or its availability got destroyed here. That is what here irreversibility. So in this equation, let's call this is the 1. So even though exergy in minus exergy out is 0 here, we still have this irreversibility here. So from this equation, if you want to find out the amount of irreversibility that has been produced in this equation, in this process, because of the steady state, then we need to make use of this equation. Here this is not 0, okay, only this is 0. Now I will take this one TR, and this TR we have a Q dot is produced here, and I am supplying this energy to produce useful work in a reversible cycle, and this is a T naught here, and we produce some amount of work here. This is a dot, and this is the maximum. If it is a maximum, if I consider this as a reversible cycle. So whenever I consider reversible cycle in a corner cycle, what happens? We produce the maximum. And what is the availability? Availability is nothing but if you make use of the available potential to produce a useful work, and if it is a maximum work, then that is the availability here, and that is what we are trying to produce. So how much W max we can produce by using this TR and Q dot given to the system here. And in the corner cycle, what happened? The efficiencies, if I equate the efficiencies, then 1 minus T naught by TR is nothing but W max dot by Q dot here, because this is the rate of heat that is given to the system, and from this one W dot max equal to Q dot into 1 minus T naught by TR. So here what is this W max? W max is availability, and its rate is availability rate here. and if I substitute these values here, q dot is a 8.25 kilowatt, that is a kilo joule per second, and T naught is 300 and Tr is 1500 here, and if I substitute these values, then I will get 6.8 kilowatt here.